Hello and welcome to yet another video of Cornerstones of Math. Today's video is closely related to my last video, which you can check out by clicking the link in the description or at the top right corner. In that video, I carried out the following summation. The summation an is defined as the summation of binomial coefficient or combination n choose n minus k divided by n plus 4 choose n minus k, where k changes from 0 to n. In my last video, I used the following method. First, I essentially made an educated guess based upon either pure trial and error or algebraical manipulation. The guess was that maybe the summation an can be expressed as n plus 5 divided by 5 for all natural numbers n. And then I proved my guess in a logical manner using mathematical induction. Basically, we assume that am is equal to m plus 5 over 5 for some natural number m, and then prove that am plus 1 is equal to m plus 6 over 5 using our induction hypothesis about am. This brings us the new question. Perhaps we can actually solve this problem by a method that does not rely on guessing. I am of course talking about the recurrence relation method, that is, finding the relation between an plus 1 and an. So let us find the recurrence relation. If this is the expression for an, then an plus 1 is given as the summation of n plus 1 choose n plus 1 minus k divided by n plus 5 choose n plus 1 minus k, as k changes from 0 to n plus 1. This summation contains one more term compared to an. So let's split the summation into two parts. The first part where k changes from 0 to n, and the very last term where k is equal to n plus 1, which is n plus 1 choose 0 divided by n plus 5 choose 0. We want to change these binomial coefficients to something that are present in the expression for an. This can be done by using the following famous property of binomial coefficients. N choose k is equal to n over k times n minus 1 choose k minus 1. Applying this formula, we have now n choose n minus k here multiplied by n plus 1 over n plus 1 minus k, and in the denominator, now n plus 4 choose n minus k multiplied by n plus 5 divided by n plus 1 minus k. And the second term just gives 1. In here, these parts containing k cancel out each other, so n plus 1 divided by n plus 5 can come out to the front, then sigma n choose n minus k divided by n plus 4 choose n minus k, then plus 1. Notice that this part right here is equal to an, so we have n plus 1 over n plus 5 times an plus 1. So this is our recurrence relation. But the problem is, this is a rather unconventional recurrence relation, not appearing that often in textbooks or other basic level materials. So can we solve it? Yes, we can, with a little help from what you might have learned in basic courses. That is, we must somehow make use of the simpler recurrence relation to solve this more complicated one. The simpler version that I'm going to use is the recurrence relation of the form an plus 1 is equal to some function of n fn times an. The standard method to solve this recurrence relation is to substitute n with 1, 2, 3, so on, up to n minus 1, and multiply all of them. So n equals 1 gives a2 equals f1 times a1, n equals 2 gives a3 equals f2 times a2, and so on, and n equals n minus 1 gives an equals fn minus 1 times an minus 1. If we multiply all of them, we will obtain the general term an is equal to the product of f1, f2, f3, so on, up to fn-1 times the first term a1. But what we have here is a bit more complicated because now we have the constant term 1. So can we somehow convert this into simpler form that I just explained? The key idea here is to find a sequence or a function gn such that an plus 1 minus gn plus 1 can be expressed as n plus 1 over n plus 5 times an minus gn. Because then sequence an minus gn is in this special form, which can be solved by substituting numbers and multiplying them. So let's see if there's such gn. Rearranging this relation gives an plus 1 is equal to this term, n plus 1 over n plus 5 times an, and this term moved to the right hand side, so plus gn plus 1, and then this term minus n plus 1 over n plus 5 gn. Let's compare this with this. Then you can easily notice that this part must correspond to constant term, hence it is 1. That is, gn plus 1 minus n plus 1 over n plus 5 times gn must be 1. That is, if we multiply n plus 5, we have n plus 5 times gn plus 1 minus n plus 1 times gn equals n plus 5. Let us try to find gn in a polynomial form because that's the simplest. You can easily realize that it is impossible for gn to be a constant function, so let us try the linear function, that is, gn is equal to pn plus q. So if we write this equation again, we have n plus 5 times gn plus 1 is pn plus p plus q minus n plus 1 times gn is pn plus q, and this equals n plus 5. If we expand the left-hand side and rearrange, you can easily notice that n squared terms get cancelled out, so the highest degree term is n, and the coefficients are 6p plus q from the first term, and p plus q from the second term. And as for the constant term, we have 5 times p plus q from the first term, and just minus q from the second term. So this equals n plus 5. If we simplify, we have 5pn plus 5p plus 4q equals n plus 5. So by comparing coefficients, we have 5p equals 1 and 5p plus 4q equals 5, which gives the value p equals 1/5 and q equals 1, which gives gn equals 1 over 5n plus 1. Therefore, there indeed exists such sequence gn. In other words, we indeed have the relation an plus 1 minus gn plus 1 equals n plus 1 over n plus 5 times an minus gn. So we substitute n with 1 to 3 dot 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 n minus 1 and multiply them, which gives this set of relations. And if we multiply them, we will obtain an minus gn equals a1 minus g1 multiplied by, if we simplify this part, you will obtain 2 times 3 times 4 times 5 divided by n plus 1 times n plus 2 times n plus 3 times n plus 4. The thing is, for this special problem, we don't even need to simplify this part, because let us take a look at a1 minus g1. a1 is just this simple summation where k changes from 0 to 1 of 1 choose 1 minus k over 5 choose 1 minus k, which is this. which gives the value 6 over 5. And from the expression for Gn, G1 is equal to also 6 over 5. That is, this A1 minus G1 is 0. This means that An is just equal to Gn, which is 1 over 5n plus 1, which can be also written as n plus 5 over 5, which is the same answer that we obtained by guess in the last video. But there's actually another method, which is a direct calculation using factorial notation of binomial coefficients. This method is suggested by one of my viewers, Griffith-Vento1, so huge thanks to Griffith-Vento1 for providing another method. This method uses the famous factorial notation of binomial coefficients, which is that n choose k can be calculated by n factorial divided by k factorial times n minus k factorial. With this, let us take a look at the term that we must add up, n choose n minus k divided by n plus 4 choose n minus k. Notice that n choose n minus k is equal to n factorial divided by n minus k factorial times k factorial, and n plus 4 choose n minus k is equal to n plus 4 factorial divided by n minus k factorial, and we subtract n minus k from n plus 4, which will give 4 plus k factorial. So we can cancel out these n minus k factorials. Then we have n factorial times 4 plus k factorial in the numerator, and n plus 4 factorial times k factorial in the denominator. This equals, from 4 plus k factorial divided by k factorial, we obtain k plus 1, k plus 2, k plus 3, k plus 4 at the numerator. And from n factorial and n plus 4 factorial, we obtain n plus 1, n plus 2, n plus 3, n plus 4 in the denominator. Therefore, the summation an equals the summation of this term. We can take out 1 over n plus 1, n plus 2, n plus 3, n plus 4 to the front. And inside the sigma, we have k plus 1, k plus 2, k plus 3, k plus 4. In order to convert this into a telescoping sum, we multiply k plus 5 minus k, which is just a constant 5. This means that we need 5 here in the denominator. Then, distributing like this, we can write this as k plus 1, k plus 2, k plus 3, k plus 4, k plus 5 minus k, k plus 1, k plus 2, k plus 3, k plus 4. This is a telescoping sum where we can cancel out terms. So in the end, we only have this term and this term, which is 0. So we have n plus 1, n plus 2, n plus 3, n plus 4, n plus 5 divided by 5, n plus 1, n plus 2, n plus 3, n plus 4, which in the end gives n plus 5 over 5. And that's all for today's video. Thank you all for watching. Please hit that like and subscribe buttons if you enjoyed this video, and I will see you in another video.